Hello, all, and welcome to Critical Faculty. Today, I'm very, very excited having one of my favorite guests on the show today discussing a brand new book that is about to launch in few days. Please join me in welcoming
Today
Dr.
discussing
Lawrence
a brand
Krauss.
new book that is about to launch in.
Hello,
There you go.
Dr. Lawrence. How are you?
It's good. I'm sorry you were playing in two different places. I'd opened you up somewhere else, so we were
That's
hearing.
all right. That's all
Okay,
right.
good. Anyway, nice. Yeah, it's great to be back with you again, and not to hear myself in stereo and triplicate. So that's great.
Well, thank you so much. I've just literally like 2 hours ago, I finished your fantastic book. It's a brilliant book. It's very focused, and it doesn't really beat around the bush. It picks up mysteries around the world, and I was actually amazed that you weren't just focusing on cosmology and physics, but you've spanned out for the first time almost.
I've done it. I've touched other topics every now in a variety of other books, but I wanted to talk about the frontiers of the edge of knowledge and that frontiers of what we know, and I wanted to mostly also hit the key questions that everyone asks about the world before they get afraid of science, and 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 so those questions include lots of questions from physics, but they also include questions about the origin of life. Are we alone in the universe? And of course the deepest question is sort of what makes us us. And it was a challenge and fun to be able to do that. Obviously, I'd run several meetings on several of these topics, but it was a chance for me to push myself, which I like to do in each of my books, because it's easy to write the same book over and over again. But if I can expand the areas I'm touching, then it forces me to get up to date on things that I may have studied at an earlier time. And so it was a challenge, but fun. And I'm very happy with how it turned out. I'm really happy to be here with you. You're one of the few people that's already gotten a chance to either hear it or see it, and so it's fun to be able to talk to you in advance of the book coming out.
Thanks very much. And folks, the description of the book is in description of the actual video around here. So it's you can see the link. It's the Amazon link. The book is about to be released on the 9th of May. You can get it as a hardcover, on audio, as an Audible, or on Kindle as well. So please make sure to visit that link provided and check that fantastic book out. I can tell you that this is one of my favorite books that I've read, at least in the last couple of years. It's very focused, and I've got so much information out of
Oh,
it.
well, that's wonderful of you. By the way, I should say, since I know you're out of Australia, um, that I just got this in the mail the other day. This is the British version, which this is the version that will appear in there'll be people can get in Australia. So it just came to me, arrived yesterday actually by mail. It's called The Known
Oh,
Unknowns in Australia and England. It's the British version.
I
So
like the red color right instead of the blue. So
yeah, it's red and blue. Yeah, so
yeah,
the blue is right behind it, so you can compare it.
right.
Anyway, so just so people know that if they're there, I just occurred to me since I know you're in Australia. Anyway,
It's fantastic. One of the things that it was quite exciting for me for you to write about consciousness and life, because Edwin Schrödinger wrote a book called "What's Life," and sometimes when you get an outsider that was not sort of not looking at the problem, because maybe sometimes you're very close to the problem, that it is right in front of you and you can't see it, and it takes an outsider to uncover something new.
well, yeah, that and the fact I agree with you, and the fact I address that actually in the chapter on life, because people may say, "How dare you, physicists, write about this?" First of all, as I say, my institute has run a number of workshops on the origin of life, but more importantly, the early scientists who were involved in thinking about what the nature of life is, and ultimately the development of genetics, were all initially physicists, not just Schrödinger. Schrodinger's book, inspired Jim Watson,
Mhm.
and then Francis Crick, who was the other one from DNA, was a physicist, and um, what's his name? His name just escaped from me. One of the major people who won a Nobel Prize for early genetics won it while he was a physicist. Yeah, in fact, um, Peter Medawar, I think. Yeah,
Right.
yeah, and no, that's not wasn't Peter Medawar. I'm sorry, my mind is gone, but I'm going to have to now. I've got to look it up because it's going to drive me nuts if I
That's happens to me.
because Max Delbruck, of course, he was a wonderful physicist, but actually. won the Nobel Prize for work he did while he was still in the physics department before he moved into biology department. And that so there's a great tradition of physicists sort of being involved in that. And and in fact, I once did an event with Jim Watson, who we talked about. It was in honor of Max Delbruck, his 100th birthday, and I often wondered why. This is aside from the book; it's not in there. But Max Delbruck was lauded at this event as a great biologist, but no one talked about his life as a physicist. He'd actually done some very important work, and there's a kind of particle scattering called Delbruck scattering. And I asked Watson why Delbruck never seemed to talk about his life as a physicist, and apparently he was roommates, or at least a colleague of a brilliant physicist who later on wrote a lot of things, and in fact, sort of was derided. He was one of the reasons I became a scientist. He wrote many popular books for kids on science, and according to Watson, Delbruck was embarrassed because he never thought he was as bright as this other guy was, so he didn't mention his physics. Yeah. Anyway.
There's a linkage. One of your very last sections of the book is a conversation about life, and when you talk about biology, there's always a conflation between biogenesis and evolution. And I'm going to start from the very beginning, because the same conflation is I find similarity of people talking about the Big Bang or the Big Bang model as the beginning of life, rather than the evolution of what happens after t equals 0. So it's almost the same conflation exists in cosmology, where people thinking, can you tell me what happened before? And this is where time becomes a bit tricky.
and to try and even using the word like prebiotic molecules is almost doesn't mean what does pre-biology mean when biology doesn't exist? Well, it's chemistry, and that's the real forefront. There was a lovely review of my book that appeared, and he said he wished I'd spent more time on evolution. But the deep questions right now are not, the biggest questions are related to the origin of life, and the key question is to try and figure out if just normal chemistry, how normal chemistry can produce what seem to be complex biomolecules, and it defies our intuition. And I love that, because science is all about defying our intuition at the forefront often. And what you discover is, in exotic environments, chemical reactions that you might think would not drive simple molecules to form complex molecules can actually become anthropically favored. And so that under unusual environments, you can actually build up, as John Sutherland and others have shown, this sort of a route potentially to even build up RNA, the complex biomolecule that we think was the original, that is most likely the original precursor before DNA to what we call an RNA world, because RNA has basically on its own all of the elements that you kind of need to get a self-replicating molecule that has a metabolism, because RNA acts like an enzyme, as well as storing genetic information. And that discovery by actually my former boss, when I was at Yale, the dean of the college was Sid Altman, and he was one of the two people who first discovered that RNA was an enzyme. And I was kind of shocked when he won the Nobel Prize, because I figured he was just a dean.
Yeah. Now, with the theory of time, we'll start with time, because time.
I know we're jumping to life. I keep backing it back to. Let's go back to time. We don't have much time.
One of the most valuable, most expensive commodity that we have around, but we are happy to spend an hour watching Kat's video and spending it away because it's relevant and it's because it's amusing. But we've got two theories, the turn of the century, last century, there were conversations about what's the nature of time. It seems to be quite elusive. It seems to be something quite intuitive. We understand it as an era of time, but when you probe it under physics, you ended up with two theories, two popular theories, the A and B. One that says the A theory that presentism, only what exists really is the present moment and versions of it, and the B theory, which is actually the past and the future do exist, but they're all exist simultaneously together along with the
Well, it's
present.
not sure they exist simultaneously. They exist in that itself. That's the problem when you talk about time. The linguistics, the semantics break down because the future and past don't exist simultaneously. But some people would say that all of time exists, is in existence. And if you think of a sort of a super space picture of the universe where space and time are tied together, the wave function of the universe is described for all of space and all of time at any instant or any. Again, see, I'm using the wrong words. And there's that argument, therefore, that time is an illusion. I've never found that argument particularly compelling, by the way. Um, Primarily for the reason I mentioned in the book. Uh, I was 5 minutes late in coming onto your program because I couldn't find the right link, and that 5 minutes was really important to me. It wasn't an illusion to me that I was late for your podcast. So whether in some meta description the entire history of the universe is somehow prescribed or not in some wave function or the set of possible universes is described in some wave function is of less interest to me in the sense that operationally the notion of time itself. Was there beginning, did our universe have a beginning? Was time eternal? Will it be eternal in the future? Those questions are really, I think, the questions that grab people. Um, and and if time is an illusion, as I say, maybe it is in some sense, but it really isn't. Art, as to take it back to the end of the book, some people say consciousness is an illusion too. But again, as I say there, if you get kicked in the shins or you lose or your lover leaves you, your sense of self is certainly affected.
Absolutely. Is there a distinction between the breaking of the symmetry at the very beginning that causes the arrow of time where everything passes and we go through the different moments, and the time that is entangled with space as a dimension, using space time?
Well, that you're hit on the key point, one of the key mysteries, and it really is a mystery that arose as a result of general relativity and special relativity. Time and space are tied together; they're not separate entities, and yet time seems to be very different. Time has, as you say, a unique arrow as far as we can see. You always go forward in time; we don't go backward. But space, I can go around in a circle. There's some essential dichotomy there. Now, general relativity actually doesn't have that problem in principle because it says you can design space times where time travel is possible. If you write down the proper mathematical type of energy and momentum, because in general relativity, energy and momentum determine the nature of space time, which then determines the evolution of energy and momentum. But if I can write down the proper form of energy and momentum, I can produce a space time that allows time travel. But then the key physical question is, well, I can write that down mathematically, but can I produce it physically? And that's still unknown. That's one of the open questions. And there are arguments that should suggest that probably you can't in most conditions, but we don't know for certain.
Yeah.
So, but that dichotomy, that apparent uniqueness of the time direction where space can go back and forth, certainly has been a puzzle to anyone who's thought about time, and it really becomes relevant in the near a black hole or inside of a black hole, because as I described, in some sense, the relationship between the identification of time and space flip when you cross the event horizon of a black hole. Space becomes time-like and time becomes space-like in the sense that once you're inside the black hole, there's a unique direction of space. No matter what you do, you always go in the direction towards the singularity. No matter what you do, it's always in one direction. Space becomes inside of black hole. Space becomes time-like, whereas time becomes kind of space-like because if you look up what you would call the up direction, you're looking at all the rays that have come from the entire sort of history of the universe here. And if you're looking in the other direction, you're looking at rays that have entered the black hole before you. And so you can see backwards and forwards in time, in a sense. Time appears to be infinite because the entire future history of the universe, if you wish, all the rays that are going to come in the entire future because of time dilation near the event horizon of the black hole, they all come in more or less around the same time. So you'll constantly be able to see until you get destroyed in the singularity. If you in that direction, you'll constantly be able to see time in one direction, and you'll constantly be able to see light rays that came in before you. So that flipping of space and time is really kind of fascinating and not yet fully understood, because we don't understand what happens at the singularity itself, which is the end of time and space.
Right. One of the issues of time travel that I was thinking the other day, that time isn't just the time that you look at your watch and say, well, I've got an appointment in 15 minutes. It's literally the measurement tool of changing of events and changes in the system.
That's
And
what time is. It determines events. I mean, space-time is a playing field of dynamics, and what time and space both are labels of events. And therefore time really does, whether it's imaginary or not, does play a role, because we have to define that playing field of events in terms of space and time. And in fact, they're linked in another way, as I point out. Many people have thought of time machines. Many people would like to invent a time machine. But H.G. Wells, of course, his famous story about a time machine is wonderful. But what people don't realize is that you need a time and space machine. Because if I were to go back in time an hour and show up in this point right here where I am now, the Earth would long ago have moved in its orbit. I'd find myself popping out in empty space, which wouldn't be very healthy. So I'd have to be I have to have a time and space machine. Just a time machine would be disastrous.
Yeah. One of the things, because a lot of paradoxes also will emerge, because you'd be going against entropy, going back in time. And if you're going back in time, you're going against entropy, and even going into the future, you're changing potential events that might actually affect the past in a retrospective way, which is
well. That's, I mean, some of my favorite science fiction episodes involve that, because of all this famous paradox, the most famous paradox, which I call the grandmother paradox. So I'm not the only one to call it that, but commonly known as the grandmother paradox. What happens if you go back in time and kill your grandmother before your mother was born? Well, then your mother was never born. But if your mother was never born, then you were never born. And how did you go back in time and kill her in the first place? So in Star Trek, my favorite episodes of Star Trek all involve that kind of time paradox where changing the past changes the future. And of course, there's that the famous series of movies with the DeLorean involved exactly that. Back to the Future, changing the future or changing the past because you change the future. It's really it's fascinating. I mean, it's fascinating, but there's always if you think about it, actually, it's even more paradoxical than that. I mean, one of my favorite episodes is in Star Trek involves going back in time and finding part of Data in a cave, and the minute they find it and do something, Data in the future changes. But it's not. But it's like it wouldn't be that way, because they would have found it centuries ago. So it always would have been that way. It wouldn't be like suddenly it would change because they went back that moment, because they were. And so thinking about time travel produces, it's great fodder for writing stories, and it's very confusing for physicists. And that's
and of course,
some physicists have said time travel in a sensible universe, backward time travel is impossible. And I think, I forget if I put in the book, but I've said it often, that when I wrote the physics of Star Trek, Stephen Hawking wrote the foreword, and he said time travel was impossible, because if it was possible, we would already be inundated by tourists from the future. And then I countered him by saying they went back to the 1960s and no one noticed. So, but a lot of physicists, including Stephen, have argued that while mathematically general relativity allows time travel, physically there are certain conditions on the nature of energy that preclude you creating a configuration of mass and energy that would allow time travel. And I think a lot of people think that's likely, but there's no proof of it.
Yeah, obviously that is a problem as well when you think about causality as linear, because we know now that sometimes causality few things can conspire to cause an event rather than just the one thing. And
but there's still causality. I mean, as far as and that's the problem. If you have time travel, you throw out causality. But once again, the universe is the way it is. So maybe we have to throw out causality. I mean, we don't like it, but just like if the universe had a beginning, we really have to throw out causality, right? Or at least the classical notion of cause and effect. If time begins, if literally time begins, not just our universe, but if time emerges out of the Big Bang, there was no before. There literally was no before. It's not even a question you can ask that it makes sense. But if there's no before, then the notion of cause and effect at the point of the singularity, at the point of formation, breaks down because there was no cause, because there was nothing that preceded the effect. And philosophers and some theologians hate that idea, but whether they hate the idea or not, it may be true.
Yeah. Recently, Professor Brian Greene was in Melbourne, and I attended his speech. And as you know, he's a proponent of the superstrength theory. I was quite shocked, and I've actually loaded my question on my channel I've asked him the question, because he alluded in his conversation to that he actually believes now that time and space began at the Big Bang. And as you know, that is not consistent with believing or thinking that the superstrength theory is true. So I've asked him the question. He said, look, I'm a very, very rational superstrength theorist. And he actually kind of alluded that he actually believes in the Big Bang model. And
the string theory doesn't say the Big Bang doesn't happen. It's supposed to explain the initial conditions, because that's all string theory is. If it were correct, it would be a theory of quantum gravity that would allow us to understand that initial singularity. It hasn't. Let me make it clear. It hasn't done that. It hasn't really given us any knowledge about the nature of the origin of a universe that we didn't have before. A lot of speculation. But Brian, is a reasonable scientist. But I think he's still maybe when string theory has been very good to him, so it's probably hard for him to abandon it. So.
Yeah, I was surprised throughout his conversation. He's almost trying to say, "Well, I want to go back to being a classical physicist," and he wasn't focusing so much on the superstring theory, which is quite interesting. But
because he hasn't done much since he wrote a long time ago, so it's probably not in his interest to focus on.
Yeah, but I've been reading your stuff quite recently as well, and I think you might have changed a little bit, because I remember 3 or 4 years ago, superstring theory was not as as convincing, but it seems that you maybe grew to like it a bit.
No, people just interpret things I say differently. String theory is well motivated and fascinating, and it still is the best candidate for a theory of quantum gravity. It just hasn't achieved. It's not clear. Well, it's not clear we even know what the theory is. So it's not as the only thing I've ever been opposed to is the hype. But I appreciate string theory has produced mathematical insights that may be important. That already have helped us in various areas of physics, and may ultimately be important for understanding the black hole information paradox problem. So string theory has produced a whole bunch of interesting ideas. It just hasn't done what it claimed it would do in the first place.
Right.
So that I think has always been the same. I've never been as hostile to string theory as some people think. I'm just hostile to the claims, outrageous claims of things that it hasn't done. Just as recently I wrote an article that was critical of astrobiology because there are so many claims that are unfounded that field makes.
Yeah, well, which is going to take us to space now, because obviously when we talk about time now, we're going to have to talk about space, even a singularity. When we talk about a singularity that is eventually going to expand, did it occupy a certain space? Does space need to exist for that singularity?
Space-time doesn't need to exist. I mean, that was a central point of my book, A Universe from Nothing. Space-time does not need to exist, and it can spontaneously come into existence when there's no space and no time. If gravity is a quantum theory, space and time are the quantum variables of gravity, and quantum variables fluctuate, and so you can suddenly create a space-time, just like I can suddenly create a particle-antiparticle pair in space due to the laws of quantum mechanics and relativity. Most of the time, those particle-antiparticle pairs annihilate in a time scale so short we can't see them. We call them virtual particles, but we know they're there because we can see their effects. But every now and then, if a particle-antiparticle pair pops out in a certain condition, in a certain configuration, say near a black hole, their total energy can be zero. And if their total energy is zero, then they can continue to exist as real particles. And that's part of what's related to what's called Hawking radiation near a black hole. But the same is true for a universe. If you had a universe pop into existence, a space-time pop into existence that didn't exist before, and if the total energy of that system were zero, then there'd be nothing stopping that universe from persisting. And as you've heard me say before, if you asked what would universe look like that emerged in that way from nothing,
Exactly like
and survived 14 billion years, it would look just like the universe we live in, which doesn't prove it's the case, but it certainly makes it suggestive.
Yeah, it's obviously a possibility. Now, with spaces is a very interesting proposition as well, because we think of space, we think of being able to move up and down, right and left, forward and backwards. But Einstein discovered some interesting relationships with space and how it interacts with and causes gravity, and namely the curvature of space caused by gigantic, big, massive.
Well, everything curves space. You're curving space around you right now. You're just curving it a little bit.
Yes, and it changes things, and gravity is one of the things you've talked about throughout your book, because it seems to be that the weakest of all forces. It seems to be the one that is causing us the most headache.
Yeah. Well, I think it's causing us the most headache because for two reasons. First, because it's so weak, and therefore it's very hard to measure properties of general relativity where gravity is strong enough to see the deviations from Newton. And it's so weak that we can't even hope initially to be able to see the effects where quantum gravity are important. There's only two places: the beginning of time and the center of a black hole. And that's why there's so much interest in those two things, because we can try and use what we can see about the universe and maybe what we can measure about with black holes or black hole analogs to try and test ideas that will maybe give us insight into that nature of quantum gravity. But it's because gravity is so weak that it's incredibly difficult to test any of our ideas for going beyond general relativity. And that's why it gives us headaches. And the great experimental discovery of gravitational waves, the triumph that it was just unbelievably difficult. The LIGO experiment we've talked about, it's just amazing what you had to measure the change in the length of two 4-kilometer arms by 1/1000th the size of a proton. It's amazing that it could be done, and it was done. But that was, those incredibly weak effects came from the collision of two objects that were 30 times the mass of the sun.
Yeah.
And even all of that collision then produced those little ripples in space and time, but we were able to measure them. And
it's almost like a cosmic tsunami. We're talking about tidal waves caused by the collision of two black holes. This is incredible.
It's a tsunami, but it's a very small tsunami. Yeah, right near the black hole would be significant, but the gravitational fields would already be significant. But yeah, so it's a tsunami that changes the height of the wave. However, if you want to think of it that way, is 1/1000th the size of a proton.
Yeah.
So it's a tsunami that we don't notice. In fact, there are such tsunamis going through us probably all the time. And we had to build a very careful experiment to be able to do that. And as I've, again, talked about at length before, it's fortunate. I mean, we've seen many now. I think they see about one a week. But the original detection of two black holes colliding that was done at LIGO was made 3 hours after they turned the machine on. If they waited for 4 hours, that signal, which had been traveling for 1.5 billion years or so, would have gone past the Earth, and they would never have known it was there.
Yeah, as you've rightly mentioned, it seems like the solution of the mysteries, we're going to need a lot of luck. I think there's a lot of luck.
And as I pointed out, gravitational waves could play a role in that luck, because with a colleague of mine, Frank Wilczek, I showed a while ago that if we could see gravitational waves not from colliding black holes, but from the beginning of time, from this period called inflation, if we could see gravitational waves from inflation or detect them, then it would prove that gravity is a quantum theory, which is still not known for certain, because one of the big questions, all of these things, the string theory and everything else, is predicated on the idea that gravity is a quantum theory. But maybe it's not. It's another one of our known unknowns. We don't know. And it would be nice. Most of us think it is. but thinking it is, or hoping it is, or believing it is, isn't science. It's science is testing to see if it is.
Because even with the James Webb, we can't see past the CMB, the 380,000 years old
Well,
situation.
well, James Webb won't even see that far. You need microwave radiation, which we can use other detectors to look at that CMB. And you're right, but with electromagnetism, you can't see past that earlier than 300,000 years. But we can look at remnants that leave an imprint on that microwave background radiation, and gravitational waves would do that. If from earlier times would leave an imprint, or might leave an imprint. That's the point, and it's a big might.
Any new tools conceived that we can go beyond the CMB event? Like
Well,
actually
sure we
see
can. I mean, we can. Well, first of all, as I said, we look at imprints on the CMB radiation that was generated when the universe was 300,000 years old. But those imprints could have been signatures of events that happened at much earlier times, and we think, in fact, that the small fluctuations in the CMB, which later on formed galaxies and stars and planets and you and I, those small fluctuations which you measured, those fluctuations in temperature, we think they're caused at the beginning of time by inflation due to quantum fluctuations. So that's an imprint that's written right there. Well, maybe there's an imprint due to quantum fluctuations in gravity from the beginning of time. But there's maybe other ways to even not go back that far, but electromagnetic radiation, the universe was opaque before 300,000 years, so you can't look back. But if we could detect these particles called neutrinos from the Big Bang, we'd be able to look back to a time when the universe was about 1 second old.
your favorite particles.
Yeah, my favorite particle. And I thought for many years trying to think about how to detect cosmic neutrinos, and people always hope to have ideas, but no one's been able to do it so far.
Well, we go to the matter of matter, of what constitute matter, because that idea started with Democritus, who thought about that there is got to be something that is indivisible, something so fundamental that you cannot divide any further. And we found the atom. We thought that was it. What happened then?
Yeah, what always happens is we look further, and another layer of the universe gets unveiled, and atoms are made of protons and neutrons, but protons and electrons. The protons and neutrons aren't fundamental; they're made of quarks. And now, as far as we know, quarks and electrons are fundamental, but we don't know for sure. And so we want to keep exploring.
So even with the discovery of the Higgs boson, the thing that gives everything its mass, apart from a bit, I guess, photons, because that's why they're massless. They don't interact with that. Can we expect something, a discovery like that? Another elementary particle to be discovered? Maybe dark matter is a candidate.
Well, not only are we expecting it, a lot of people are devoting their lives, their scientific lives, to doing it. When the Large Hadron Collider was built, the one in Geneva, we hoped it would find the Higgs. Many of us thought it wouldn't. But it was actually a hope that many people thought before that it would be much easier to find the particles that make up dark matter. Not coming from the cosmos, but creating them by the collisions of particles in the laboratory. And the Large Hadron Collider is on a new run in Geneva right now, to hopefully look for these candidates. It hasn't found it yet. Somewhat disappointing to many of us. I'm just going to run. Hold on 1 second. My dog wants to out this door here. I'm going to let him out the door.
Sure. Okay. I'm sorry, folks, what we're discussing today. I'm very sorry to disappoint you. We are going to be discussing Dr. Krauss's book mainly today. So it's going to be very difficult to take outside questions outside of the book.
Back. I just wanted to let him outside my door. He was sleeping here in my study, but he wanted to go out. I don't think he likes talking about the Large Hadron Collider, so he always leaves when I talk about that.
We know that dark matter exists because we have detected its
we detected its effects, and I have to say, some physicists say, well, it's not dark matter. It's due to a change in gravity. Somehow gravity. I think most physicists don't buy that argument, and there's good reasons to think we need these new elementary particles that are not protons and neutrons. They solve many problems in cosmology, we know that if gravity acts the way we think it does, then our galaxy and all galaxies weigh about 10 times more than they should, 5 to 10 times more than they should, and then that's material doesn't shine, and that's why we call it dark matter. But we don't know what it's made of, and there are lots of good candidates. I spent much of my scientific career not only thinking about possible candidates, but thinking about ways to detect them.
Last bit on the matter, then we go to life and consciousness. Is dark energy, the force that is responsible of the acceleration of the expansion of the universe.
Yeah, the big mystery, the biggest mystery in physics, really.
Yeah,
Why is the dominant energy in the universe reside in empty space? We don't know. And that when you put energy in empty space, it's gravitational repulsive, so it's causing our universe to expand faster and faster, and that's going to produce a very different future. And we don't understand that at all. I'm going to close this door again because I'm hearing noise out there.
that's okay.
There's two questions about dark energy. First of all, why is it there? And why is it so small? Why is it, even though it's the dominant energy of the universe, if you try and think of it from a fundamental perspective, it's 120 orders of magnitude smaller than we would have expected if it's be non-zero. So it really is the biggest mystery in physics, and we don't have the slightest idea. I mean, many of us I proposed ideas myself, but I suspect they're all wrong, and we'll probably need a quantum theory of gravity. I mean,
Right.
obviously, dark energy is something that matters a lot to me. I think about it because I first argued it was there now 28 years ago. But it will determine the ultimate future of the universe. So it's kind of important, and it defies all expectations because it means if you look at space and get rid of everything in space, it's empty. It weighs something, and that's flabbergasting.
Yeah, yeah. There's another item on space that it was very important to me because I felt reading your book that you might have changed your position tiny little bit about the shape of our universe, whether it's flat, open, or closed, and you seem to be a bit more agnostic about it rather than just say flat.
I try to be agnostic about everything that I haven't tested, and so I may every now and then I fall in the depth of belief, but I try and get out of those depths pretty quickly. I think I'm not sure that's changed. Look, the universe on the scales we can measure it is definitely flat, but the key question is on its largest scales is it flat? And there are good reasons to think ultimately, if our universe was created from nothing, that it's closed, that it's actually closed in on itself. But on a scale so large, and now with inflation, blown up to, just like blowing up a balloon very, very large, it looks flat. So we'll probably never be able to measure those departures from flatness. But I suspect on the largest scales, it's probably closed.
Can a universe evolve into being flat, or it must start flat?
Closer and closer to being flat. Just like a balloon. Look, it's exactly like a balloon. You blow it up, it looks flatter and flatter and flatter. If you're in Kansas, if you're in Australia, the center of Australia, except for Ayers Rock or whatever, it's flat, right? And so if it's big enough, it's going to look flat. So things look flatter and flatter and flatter. But ultimately, if it's closed on the largest scales, it's always closed. You don't. Classical processes can't make a closed universe into an open universe or whatever. They can just drive it closer and closer and closer to the boundary. Quantum processes may be able to jump between them, but that's a different story.
Yeah. Of course, when you try to explain to people that it doesn't expand into anything, this is where the imagination stops because nobody can conceive of that.
I try, in my various books, I've tried to give examples so people can get a sense. But yes, it's very hard. But that's okay. I mean, as I've often said, we evolved on the savannah in Africa to be able to escape lions, not to do quantum mechanics or think about general relativity. It's an amazing byproduct of our evolution that we're able to do these things. But it's not surprising that some things are still pretty difficult to get intuition about because we don't experience them in any way when we're growing up, and therefore, intuitively, they'll always be confounding.
One last question about the universe, because it's going to be the segue to life. Is do you think what is the most likely situation here, that our universe is isolated and it's one off, or we are connected somehow in a multiverse or a bubble
Oh,
or
I talk in the book.
nuclear?
Most likely, I think we're part of a multiverse. Inflation generally, almost inevitably, produces a multiverse of where each universe is kind of like a seed dropping out of this background expanding space. And I think that's the most compelling picture of the evolution of things. And so I suspect our universe is part of a multiverse, and the laws of physics could be different in each one, maybe not. Um, and uh, and that's, that changes everything, right? Because it means that if our universe isn't unique, then if it's part of an ensemble of things, then maybe the conditions of our universe are special just because it's an accident.
So it does fix the fine tuning issue then.
Well, yeah. Although there's a lot of fine tuning issues that aren't really fine tuning issues, but yeah, it might fix a fine tuning issue, say, of the cosmological constant of the energy of empty space. But we don't know. But it certainly could. It's one possibility. It's called the anthropic argument.
Right.
Still a slippery argument, and I hope it's not the solution, but maybe it is. The universe again doesn't exist to please me. I discover
Yeah.
that on almost a daily basis.
Now, life is an interesting one, because even in terms of cosmology, it seems that observers are very important, and well, of all sorts, whether they actually affect things or the outcome, or they are witnessing the outcome, and therefore they're reflecting upon their conditions, and they are making inferences. They could be still wrong, but they're conscious observers of life. What do you think? You mentioned chemistry, so physics, chemistry, biology.
Yeah, that's the way it
What do you think
works.
these are the steps?
Goes from physics to chemistry, biology, and that's the nature of science. Physics is the basis of chemistry. Chemistry is related to biology, and I think if you really want to think of it temporally, I think it's exactly the same thing. Start with the universe, where really we have to describe the physics of the universe. Ultimately, when atoms form, chemistry becomes relevant, and laws of physics explain that chemistry. Quantum mechanics explains chemistry, and ultimately, chemistry results in biology. And as far as we know, that's the way it works. No one's figured that last step yet exactly. We lots of interesting ideas, and I talk about them in that chapter of the book. There's been a lot of interesting developments that suggest to me that it's possible that even in my lifetime, we may have at least a plausible mechanism for prebiotic or non-biological systems to become biological. And there are lots of interesting questions that do relate, and that's why I make comparisons to physics in both in that chapter and the consciousness chapter. Um, there's lots of when people thought of the fundamental elements of the universe, the Greeks used to look at air, earth, fire, and water. And some people say no, air is the fundamental one, and then others would say no, fire is, and of course it was like the game of rock paper scissors. Every time one would come up with one, another would say no, but this is necessary for that. The same thing happens in discussions of the early forms of life. Is it metabolism that happened first, or is it reproduction, or is it the existence of membranes that had to exist to enclose them, to separate the environment from the environment? Which is a necessary precursor? And what's been kind of realized, which I think is interesting, is the same thing that happens in the rock, paper, scissors life or air, earth, fire example, is that it could be that none of them are fundamental in the sense that they're all interrelated. And the developments that produce one are necessary for the other. Proteins are a key production of life, but proteins are necessary, are a component of membranes, and the things that develop to produce faithful replication, RNA, also is an enzyme, so it's involved in metabolism, and so it's probably wrong to separate these things and think of one of them as being fundamental. The developments that produced one most likely produce some of the others, and maybe with different functionality, because that's the other thing about life once it evolves. Um, Functionality can change. The components of living systems can change as they evolve, and that's why many of the creationists who wonder, well, how did the eye develop? You couldn't evolve an eye, but many of the components of the eye had different functionality in earlier biological systems. The bacterial flagellum is this bacterial motor that appears that could never evolve on its own, but the components of it, as various people have shown, are found in earlier systems having different functionality.
Yeah. these are obviously the proponents of the ID, the
Yeah.
reducible complexity issue,
Yeah.
and how it's been fixed, so everything's different. So I find this very consistent in cosmology, chemistry, and biology. Whenever there is a system that gets to a certain complexity, an emergent property comes out, and it sort of behaves in a different way. Is that consistent still?
Well, I mean, there's complex systems have emergent properties generally. Yes, that happens, but I mean, I don't know if it's a law of physics. Um, yeah, it depends what you mean by complexity. All of these things are semantic arguments, but generally, one can see phenomena like look, oatmeal boils when but obviously that boiling is happening on a scale of many particles in the oatmeal, and understanding the dynamics of that, understanding the electromagnetic interactions of protons and neutrons or electrons in an atom is not going to help you understand directly that oatmeal. You have to think on a larger scale. And
Uh,
so, okay.
and
Hmm.
I'll take this question to and segue to the final section of the book.
Yeah.
Do you think ChatGPT is going to affect astrophysics? Do you think it's going to make the pace faster?
Well, I don't make predictions about the future. You know that, unless the future is 2 trillion years from now. But I don't see ChatGPT itself doing it. I mean, maybe it'll help some astrophysicists who can't write, help them write paragraphs. But but the key thing that Chat GPT, as far as it doesn't understand what it's a data mining algorithm, right? And it's not answering the questions that's important. It's coming up with the questions that's important. And that I think is
Agree.
not something that's relevant. Now that doesn't mean it won't happen in the future. But and chat and things that are based on neural networks and machine learning will already help in astrophysics. Machine learning techniques have already allowed them to refine images, like the black hole image that was first seen of M87's now been refined by machine learning algorithms that can look at that data, and they've produced a much prettier picture of the black hole.
Consciousness have always been detected in brains. You need the actual organ for consciousness to exist.
Well, if we knew what consciousness was, which we still don't, but yes.
Yeah, but some people will argue. I mean, this is an interesting one because Plato and Leonard Susskind, in the holographic principle, Plato said one time that everything that we experience is the reflection and the projection of an ideal world, and the holographic principle is probably not that far away from that
Well,
principle.
maybe. I mean, you beware of pushing analogies beyond their domain of validity. But
Yeah.
you're right. Consciousness, as far as we would accept, most of us are conscious. Some of my colleagues, I'm not sure about, but most of us are conscious. And so humans we all accept that we feel like we have a consciousness, a self-awareness, a sense of self, whatever all those things mean. And I spent a lot of time in that chapter talking about that. But we don't know if that full self-awareness exists in other species. My dog, I have two dogs here sitting here, but they look like they are self-aware to me, but I'm assuming I'm anthropomorphizing. We don't know. That's an interesting question, but we certainly know that apparently you need a neural system, a brain, and also sensory organisms. And some people have argued, as I talk about in that chapter, importantly, that having nerves that sense the outside is an essential part of the development of consciousness. The notion of feelings
Hmm.
arose out of homeostasis. Yeah. Living systems need to control their metabolism, and that means also being sensitive to the environment they're in, so they can respond. If it's hot, they can try and cool themselves, etc. And that it's been argued fairly cogently, I think, that evolves into a sense of feelings, and feelings could be the precursor consciousness. And that may mean that we won't have these boxes sitting on tables that have any kind of self-awareness. They'll need to have sensory, maybe not legs and arms, but sensors that allow them to detect the environment they're in and then realize that they are part of the environment.
So the final question here for you, Dr. Krauss, and I really thank you so much for your time. You've been generous with your time today. Can consciousness be manufactured?
Well, that's my point at the end of the book, as you know, because I say I happen to think this is the case. There's so much confusion. We are so limited because we can't get it. No one else can get in our heads, and we can't get what's inside our heads outside of our heads. So if you try and study consciousness, you rely on what people say about what they're thinking. But as I show in the book, that often is an illusion. And moreover, I can't get inside your head. So Feynman said, if you can't build it, you don't understand it. And it may be to me, and I think it's reasonable that the first way we'll understand consciousness is by manufacturing it, by producing systems that somehow have self-awareness. Now, I don't think we're on the cusp of that, by the way. I'm not worried about ChatGPT myself in that sense.
Would it lead to our demise if we give it to machines? Would it lead to our demise?
Well, I mean, if you had a self-aware machine, it would change everything, and it seems to me quite likely the future of humanity would involve tying together biology and that system. Some people are upset by that, but it's just the future. So it may not be worse; it'd just be different. As I point out at the very end of the book, when in the ninth, speaking about Plato, in the 9th, 8th, and 7th centuries BC, when the Phoenician alphabet and stuff was introduced into Greek and writing arose, Plato and Socrates decried writing as the end of storytelling, and because he couldn't remember things. Well, it worked out okay. Writing didn't make it much worse. And so when people tell me that the world with AI is going to be much worse, it's going to be different. But different doesn't always have to be worse. It doesn't have to be the Borg.
Yeah. Great. I would like to congratulate you one more time for such a fantastic book. I've enjoyed it thoroughly. People, please check the Amazon link in the description of the video. Have a look at the book. This is a brilliant book, really, and I encourage everybody to read it. Thank you so much.
Thank you very much. I'm excited about this book. I think it's a great sort of successor of Universe from Nothing in a way, and I hope people enjoy it. And as always, it's been a pleasant discussion. I appreciate you taking the time to listen to the book when you had it and to ask the questions. And I hope it's been useful for your listeners. Take care.
Thank you very much. Have a great day.
You too. Take care. Bye-bye.